13.4, limits at infinity. With the rules of finite limits in place, we are now ready to consider the idea of limits at infinity. In fact, you already have experience with examples of these limits, though by a different name. Description. If the function f of x approaches a single value L, as x becomes infinitely large, then we say that the limit as x goes to infinity of f of x is equal to L. Notably, this is not a mathematically precise definition, but it is compact and nice conceptually. A precise definition demands more intricate initial conditions. By way of example, here is the book's definition. Definition. Let f be a function defined on some interval a to infinity, non-inclusive. Then the limit as x approaches infinity of f of x equal to L means that the values of f of x can be made arbitrarily close to L by taking x sufficiently large. This is a pretty good definition. If you go one step farther in mathematics, you'll find that even this definition can be improved and tightened up, and in a sense they're still trying to make it accessible even with this language. I want you to think about this though. Do you see the differences between the two statements? If not, that's fine. If yes, you should try teasing out why the bottom definition is constructed as it is, and make some notes on that observation below. I'm happy to discuss that with you further. Now, let's move on. Consider the function f of x equals x squared minus 1 over x squared plus 1. What type of function is this? Back in the day, what attributes would we have listed for it? Now, this is a rational function. We've got a polynomial over a polynomial, and there's not any real factoring opportunities here. It can't be simplified. So we would have said, yeah, the things we need to list are asymptotes, both vertical and horizontal. We would need to list zeros, and we could list other things at our option. We could list y-intercepts. Those would be the biggies. So asymptotes, zeros, y-intercept. Now, this function has no domain restrictions based on the denominator. You cannot plug anything into that denominator and get 0. So our vertical asymptote is not applicable, does not exist. Horizontal asymptote, on the other hand, for this type of rational expression, we had said if the coefficient on the numerator was the same as the coefficient on the denominator, and they had the same power, the same highest power, then the horizontal asymptote was the ratio of the leading coefficients. So in this case, that would mean that the horizontal asymptote was y equals 1. And the zeros of the function would have been x equals 1, x equals negative 1, and I am drawing that from the fact that the numerator could be broken down to be x minus 1, x plus 1. Okay, now how does this function behave as x becomes very large? Well, that was what the horizontal asymptote was all about. It told us as x went to infinity, oh, that's an interesting choice of words. Yeah, as x went to infinity, what the function behavior looked like. So according to our horizontal asymptote, as x becomes very large, the function starts to look like, we'll say starts to resemble y equals 1. That is another way of saying that f of x approaches y equals 1. And that would imply that the limit as x approaches infinity of f of x is in fact equal to 1. So there's the connection. This idea of a limit as x goes to infinity is really what we were dealing with earlier in the form of a horizontal asymptote. As I said, you've got some background with this. Okay, again, but different. How does this function behave as x becomes very small? Well, I mean, we should look at the horizontal asymptote again. How could you tweak the limit notation used in problem 4 to express this? Well, take a shot at doing that, and then I'll follow on. Now, if we're thinking about x being very small, then rather looking at the limit as x goes to infinity, we're now thinking about the limit as x goes to negative infinity. And for some expressions, we would see the function approach a different value for the horizontal asymptote when x approached negative infinity. But for this particular function, we don't. We don't see that because negativity does not differ based on the top and the bottom behavior. There's nothing in here that suddenly, when you plug in negative values, produces different behavior than when you plug in positive values. There's still a cancellation of terms. So for this case, it still approaches 1. Okay. Now, let's take a look at these limits below. Very simple functions. Limit as x approaches infinity of 1 over x. If you'll recall the shape of this graph, it looks like that. We said any time that you had a numerator that was of lower degree than the denominator, that you had a horizontal asymptote at 0. Well, correspondingly, the limit as x goes to infinity is 0. And as we've just can see in our drawing, that means that as it goes to negative infinity for this case, we're also 0. Now, let's exit the realm of rational functions and think about other functions that have asymptotes. Inverse tangent. Happily, this is one also that we've already looked at. And I want you to take a moment and dig back in your brain or look it up online. What were the horizontal asymptotes for the inverse tangent function? Now, the horizontal asymptotes for the inverse tangent function were y equals pi over 2, and also y equals negative pi over 2. If we sketch a graph of this function, we have behavior that looks something like this, with those asymptotes showing up like so. This would be pi over 2. This would be negative pi over 2. Now, what that implies then is that the limit as x approaches infinity is equal to pi over 2. And this is a case where now, as x approaches negative infinity, we have a different value, and it's negative pi over 2. We teased this next problem back in the day with rational functions, so we're going to use that to our advantage. Again, as you're looking at this from the perspective of rational functions, you should think, oh, it's got a horizontal asymptote. That horizontal asymptote will be at, because it's got the same power top and bottom, right? It'll be at the ratio of those leading coefficients. So we should expect to see 3/5 show up as an important number here. But let's do this using limit laws, because our limit laws happily all still apply. So let's look at the limit as x goes to infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. Okay, the trick we're going to use, the one that we used back in the day to first get the idea that the horizontal asymptote was 3/5, is multiplying everything through by 1 over x squared. Now remember, our choice of 1 over x squared is because the highest power term is x squared. So for our next step, we're going to rewrite this thing having multiplied top and bottom through by 1 over x squared, 1 over x squared. So we'll say 3x squared minus x minus 2, 5x squared plus 4x plus 1, and 1 over x squared over 1 over x squared. Getting ready to plow through it. Okay, so that looks like limit as x goes to infinity of, well, 3x squared over x squared minus x over x squared minus 2 over x squared. On the bottom, we'll have 5x squared over x squared plus 4x over x squared plus 1 over x squared. Now remember, we've multiplied by a form of 1, so we haven't actually changed the value of the expression. We've just changed the way it looks in a way that is useful for us. The reason that it's useful is because we now have interesting cancellation opportunities. And what we'll get at the end of the day looks like this. We'll have 3 minus 1 over x minus 2 over x squared. We will have 5 plus 4 over x plus 1 over x squared. Now, what we can do using our limit laws is rewrite this as the limit as x goes to infinity of 3 minus the limit as x goes to infinity of 1 over x minus the limit as x goes to infinity of 2 over x squared. On the bottom, the limit as x goes to infinity of 5 minus limit as x goes to infinity of 4 over x minus the limit as x goes to infinity of 1 over x squared. Now, we just did the limit as x goes to infinity of 1 over x. That, we know, went to 0. By similar token, any positive power on x is going to go to 0. So we can take all of these and say, well, they each go to 0, so in the final analysis, we are left with evaluating the limit as x goes to infinity of 3 and the limit as x goes to infinity of 5. And that's simply 3/5, better known as our horizontal asymptote. Now, I commonly will not write out the full body of this stage. Often I will stop at this point and just start evaluating the limits of each term. Keep that in mind as a useful potential shortcut. 2 problems to close. We want to evaluate the limit as x goes to infinity of e to the x and the limit as x goes to negative infinity of e to the x. The question is, how much do you remember about the asymptotic behavior of exponential functions? Always, when in doubt, sketch a graph. So looking at the graph and thinking back to your own memories, we should be cognizant of the fact that this is not not asymptotic behavior. This thing is going up all the way, and it gets faster and faster as it goes. So what we would immediately say there is that the limit as x goes to infinity of e to the x does not exist. However, the limit as x goes to negative infinity of e to the x can be captured by asymptotic behavior on this graph. We see it sliding in closer and closer to the x-axis, which means that with that horizontal asymptote at y equals 0, the limit as x goes to negative infinity of e to the x is in fact 0. Now, a different case. The limit as x goes to infinity of the sine of x. Now, this is a situation where we don't have infinite growth, but we do have a graph that is constantly oscillating. We're always between -1 and 1, but we also always are bouncing back and forth. So that's another case in which, while a function may be defined all the way out and it may have bounded behavior, the limit as x goes to infinity doesn't actually exist because we do not converge on a single value.